Our water is being ruined at the moment, isn't it?
It's damaged, yes.
How damaged is it?
No water is irreparably damaged. It's about how much it will cost to fix it. That's the simple answer to your question. So you can damage water to the point where it's black and it would be noxious smelling or terrible to look at, but there are technologies that can take any stream of water and make pure water out of it. The point is that the cost is great. And if you have clean water in your aquifers and in your rivers, it's a lot cheaper to get it to a level to drink and to use. And it poses less risk to people.
What are we actually saying here, and I'll direct this to both of you, because you have patented several things in the marketplace. Is there anything that we can patent to make it a cost-effective exercise for municipalities, mining companies, and the industry in general to give us clean water before it gets damaged as it is today, and then it costs money to clean it up?
See, actually, as Craig mentioned, treating wastewater has been very costly. Has been costly in terms of money, costly in terms of effort and materials and resources that could be available to treat this water. But I think with research, like you mentioned, we came out with publication a few weeks ago in Nature, and this has to do with membrane. Membrane, again, membrane technology is not new. But our discovery is something very unique and very new, which I'm sure the whole world should be running after this. So membrane technology, putting our membrane in the perspective, for example, people have been treating water, heating, boiling, cooling, filtering, and so on. In this membrane technology, which we've developed, we'll treat, all you need to do is make hold of water stream, the stream of water, or pipe it, pump it, gets to the membrane, it gets filtered easily. Now, membrane technology has been difficult in terms of water, in water treatment, because they experience fouling. They experience chemical polarization, which is part of fouling anyway, and it gets messed up and may not work properly. But the one we've developed has two functions, so to say. It's hydrophilic and it's hydrophobic. Hydrophilic substances are materials which accept water. The hydrophobic rejects water. So the membrane we've developed, for example, just like you have the filter in the kitchen, we can put our membrane in there and the water just go through. The side that is hydrophobic allows the water to go through. Very clear, very clean, drinkable. And then the waste gets concentrated in another stream, which you can concentrate and make use of if you want to, or discount it properly.
So this is a very cost-effective, very simple exercise.
Sure.
And you buy into this one as well, Craig, that this could be that easy to do?
Sure.
Then the obvious question I'm going to ask you is, why isn't it being done, or is it too new?
Yeah, I think that's the question I've been answering. I'm not sure if I've been able to convince people. Discovery, as you know, comes just like that. People don't really plan to discover, and otherwise we will all be millionaires, or all of us will be president at the same time. But it comes just like that. We've been working in the technology we discovered for many years. But until a few weeks ago, my students and I, we found out that something unique has been made. So it's now time for the world to use this modern technology.
Question that obviously has to come to mind, because I'm a coastal dweller. Can this membrane be used for salt water to give us clear water?
Salt water.
In other words, using more seawater,
yes,
to cleanse seawater?
Yes, yes. The membrane, like I say, is like filter. You can filter anything.
So we're saying that desalination plants, which are very costly to put up, of which we were discussing off camera, Australia is prolific in this, but South Africa is very backward in it. Desalination plants could be built cost effectively merely on the membrane system.
Very well. Actually, let me give you more of the picture of what the membrane is made of. We use polysulfone, a polymer, as the background, which we mix with carbon nanotube. And then we use polyvinyl alcohol, Now, the membrane has one side covered with polyphenol alcohol, which is hydrophilic. Okay, people have been using polysulfone for many years, even in desalination. But like I said, the salt water foul this membrane very quickly. So that's why it's costly and so on. But because of the inclusion of carbon nanotube, which is now hydrophobic, and gives strength and toughness to our membrane, so this makes it so unique and so cheap, because all of these materials we make here, carbon nanotube, my students produce downstairs there.
Is there a lifespan to the membrane?
Yeah, I think the carbon nanotube also give it a very long life span, because carbon, of course, I don't know, I can't remember the half-life of carbon. It's hundreds, thousands of years. Yeah, so that can exist for many years, and reinforcing the polysulfone with the carbon nanotube gives it years of lifespan.
So not only then are we talking about a solving of a massive problem here, we're actually talking about a maintenance-free situation as well.
Sure.
Low maintenance.
Low maintenance.
Probably low maintenance,
yes,
or lower maintenance.
Much lower.
Yeah.
Yeah.
Because what it does also is, now we use cross-flow, we put the membrane and it comes out as cross-flow system. That may be difficult to understand, but what I'm saying is, if this is the membrane sheet, for instance, and the water is tapped from wherever, from sea, from underground, from where, and gets contact with the membrane, it makes target with the membrane, flows out, so you can circulate it.
Oh, so you have to have an overflow outlet.
Yes, it's also
for the effluent.
Actually, also washing the surface of the membrane by itself.
Now, where do we dump the effluent?
And then you have the pure water on this side for the membrane, and the retentate you can recirculate.
I understand this. I've got it now. So left is effluent, right is pure water.
Yes,
right.
yes.
So we split it. Now, what do we do with the rubbish that we've got?
Rubbish is a subjective word. So whatever you're taking out should have value to someone somewhere. So as a rule, it's costly to get things out of water. So if you are a sulfate producer or a sulfur producer, you want to get sulfates or sulfur.
And if you're a cerebus or somebody who wants salt,
right.
you get your salt out.
Right. Yeah. So here you've got a system where you're extracting what for us would be a waste, but actually that can always, essentially it's a beneficiation stream. So there's a value added step. You need to then tap into a market for that. And in many instances, that effluent or your waste stream can actually pay for itself if you can get the right person to purchase it.
What other universities in the world have you contacted in association with this membrane? Because this is not a thing that should be, it's humanitarian, isn't it, in many respects?
Yes.
So it's one of those things we should share. Who have you been in contact with?
Actually, we are expecting to hear from the US government. I'm not sure from which of the agencies that this call will come. They are interested in this membrane, in the arsenic pollution problem they have in the US, and mercury. And now arsenic is used for a lot of stuff, wood preservation, arms, medical and so on. So, and their water is highly polluted with arsenic and mercury. So why they're interested now is the polluted water, arsenic polluted water, gets to the membrane, they get a pure water, drinkable pure water out, and then the arsenic is concentrated, then can be reused for the materials we just mentioned. Still in answering part of the question, late yesterday I got email from Finland. They are very interested in this membrane. I was shocked, maybe the news has gone everywhere, and they want to work with us. The idea is now, but they want to use it differently or make it differently, which we will do for them. South Africa is rich in coal, so we make carbon nanotube from coal. Now Finland is rich in wood or forest. We want to make this same membrane from cellulose. So you can see how the world is taking it differently.
Just to finish off, you have invented something that will improve dialysis at the moment.
Yes.
You were showing us something before we came that was, yeah, it's all right, have you got it?
Yeah, something here. Yeah, like that.
Yeah, now that, the blood goes through there and cleans the blood.
Yes.
But you have a better system.
Yes, essentially this is the normal dialysis membrane module, which is in the hospital. So the membrane we developed, which we were using for water contaminated with oil or acid membrane, we said can be used as well. So what we're trying to do now is, this is actually one of my PhD and a master's degree project, where we will make our membrane, because the ones we made are flat membrane. We will make it into hollow fiber and come out with this module. So now this module, for example, is used in the hospital not for so long, because it gets fouled, like I said, normal membrane. It breaks very easily because it's not tough, and the change of temperature affects this activity very quickly. And with the membrane we've made, can stand 10 bar, for example. So even the machine has problem, it will still be working. And then can selectively filter the blood, because this one they use at the moment doesn't really get everything out, or get some things out that are not supposed to be removed. But with our membrane we've developed, we can functionalize the carbon nanotube, then selectively remove what is required to be removed from the blood.
So what we're talking about is this membrane has a memory.
Memory in terms of?
It remembers things that are coming through and excludes things.
That's why, see, I don't want to go into a lot of details. That's why I use the word functionalized. The carbon nanotube, which we use with the polysulfone, can be functionalized such that if you want to take, say you mentioned seawater,
yes,
the sodium chloride. If only what you remove from the blood is sodium chloride, we make the right membrane with the right functional group, and that will take that out. Not that it has the memory on its own.
So it's not one membrane fits all.
For example, but you can make such ones that can remove so many things. Yes. I just gave that sodium chloride as an example. So the carbon nanotube is nanotechnology, which again controls the porosity of the membrane. Because this membrane you see is porous. But the one we've made, you can tailor make the porosity such that you can use it for anything. So not just only blood, acid mine wastewater, oil polluted water, the Cairo kind of water that will come from fracking also, and so on.